Yeah, thanks a lot for the introduction, and thanks a lot to the organizers for inviting me to this very interesting conference. So what I want to talk about is based on joint work with Gleb Kutuzov and Sylvain Lacroix. Well, a paper, longish paper, has already appeared on the archive, and there is some ongoing work. And yeah, I was really pleased to have such very strong collaborators for this project. So really, I experienced it as a perfect blend of expertise, and whoever has looked a bit into the paper will recognize sort of how neatly our expertise was combined into a kind of, well, at least for me, nice picture and nice result. All right, so our work returns to a very old problem. I think in this audience, I don't have to tell you about the importance of non-linear sigma models, and the integrable ones, of course, have attracted a lot of attention as models where one can go deep into quantitative studies, and there's been a lot of motivations gathered over the years, ADS, CFT, just to name one. But yeah, to be serious and honest, in the end of the day, it doesn't seem we do already have a systematic approach to quantizing and solving those, at least not to the extent we would like to. Of course, there's been a lot of activity and a lot of results have been obtained, but still, I think the vision, the idea is that we should be able to go much farther. And let me just remind of what I think still represents an obstacle and has, say, obstructed, I think, a lot of lines of attack to this problem. That goes under the name of the non-ultra locality problem. Namely, well, it's a marked difference to other integrable quantum field theories, which share some features, namely existence of a Lax pair on the classical level. So good, I mean, I recalled here the standard form of a Lax pair, how it is often written, zero curvature condition. And yeah, it follows immediately that if you take the trace of the monodromy matrix, this will be a generating function of conserved quantities. All that's good and fine, unless you, well, unless you turn to the Hamiltonian formalism for the sigma models. It still is fine for many integrable quantum field theories, like, well, Toda-like theories and several others, where you can show that this monodromy matrix satisfies some Poisson bracket relation of a standard and famous form of the form of a classical Yang-Baxter equation. And what is well understood is how to quantize such structures. So, and that opens a road towards the quantization. In particular, the quantization of these structures is, of course, well known to lead to quantum groups, etc. And say then for lattice regularization, study of the spectrum, and so on, you can use what has been learned about sort of the quantization of such Poisson brackets, their relation to quantum groups, and so on. There's a whole machinery that has been developed for some integrable quantum field theories, which, however, does not, as it stands, immediately applies to sigma models. And the main difference is that for sigma models, the Lx here, the spatial part of the Lax connection, is found to have in its Poisson brackets delta prime distributions. And people have been struggling a lot with, say, well, attempts to compute or define the Poisson brackets when there's these delta prime distributions. And well, I think it's fair to say the progress has been somewhat limited. There are some solutions that have been proposed. However, they would indicate they seem to indicate that the result is not of that simple form, but looks more complicated. And then it would mean that probably also, say, the computational relations in the quantum theory would have to be more complicated. So, okay, that's just a reminder about the problem and some motivations. All right, we looked at a particular example, namely the Klemtrik model, which has attracted a lot of interest in the past, and some generalizations. Here on this slide, which is a bit overloaded, I'm afraid, sort of the basic definitions, namely the action and the zero curvature condition are recalled. I mean, it's not really important sort of here to appreciate sort of the details of this definition. What is important maybe is there is a gauge formulation where one has G cross G valued fields modulo a certain gauge symmetry, which acts by multiplication, having group multiplication from the right. And then, okay, there's an action which has this gauge invariance. And furthermore, a second point I want to draw your attention to is that we have three main parameters. Basically, there's the K here, which can be related to the usual H bar or alpha prime or whatever you want. And then there are two parameters here, epsilon1 and epsilon2. And well, these are the important parameters to deal with. And there is a reduced representation where one has just a single group element G in the action. You see here, so that's the one given down here. You can also reduce the Lex pair the way given here. Anyway, details don't matter so much. Yeah, and if you work it out, if you introduce coordinates on the group and so on, you will find, well, some metric and a B field. So indeed, the standard form of sigma model, where everybody is dependent on the two parameters, epsilon1, epsilon2, and you have an overall factor here called K. So to give you some idea of how the target space of the sigma model looks like, we recall some, by now also kind of classical result of Fatiev on the RG flow, the one loop RG flow in that particular sigma model. Well, it took a while sort of to understand the different formulation. Fatiev had an explicit formula, and then sort of Klemtrik had this nice group theoretical formulation, and by now there's a certain industry understanding sort of how these all these different ways are related, and well, even further formulations, etc., etc. Anyway, the flow is here described by introducing a running coupling as an alternative parameter, allowing you then to parameterize epsilon1 and epsilon2, which are the sigma model or metric parameters in a particular way, as it is here on the slide. And what is also not so hard to see is that there is a limit where the beta function would vanish, therefore called conformal limit, which would correspond in this parameterization to kappa going to 1 from below. And here's a picture which gives you some idea how this kind of target space looks like in that limit, or near that limit is perhaps better to say, where yeah, it's a little bit like the three-dimensional version of the famous sausage, and it has certain similarities, in fact, relations to the sausage, but now, of course, we're in 3 dimensions. So if we're going to the UV in the vicinity of the RG fixed point by sending kappa to 1, then there is a long region in with respect to one particular coordinate. So don't worry how exactly it's introduced, which sort of is approximated by just a real line, so corresponding to a free field then in the action, and 2 circles. And then, well, there's a cap on one end, a 2-dimensional cap cross another circle coordinate. It's a little intricate sort of to really depict it in detail, because yeah, one way is sort of you can fix one of the coordinates, then you see a cigar. You can fix sort of this coordinate, which is, you might call it level-like, so which gives sort of here the horizontal extension, which is called phi. And what you then find, this is that the product of these 2 circles is sort of, well, really kind of twisted product, best depicted as a torus with a sort of twist parameter. Anyway, all these details don't matter for what I mainly want to say, just to give you some idea of the kind of model we're studying here as sort of the main example. Although I should say that really the point is to point towards generalizations. So what I want to now introduce is a formulation which also has attracted a lot of attention in the last couple of years, which will be very useful for our purposes in revealing some hidden structures, but it also serves the task to indicate some generalizations. So we will now introduce what was called affine Gaudin models, and this goes back to work of Fagin and Frankel, and then Benoit Vicedo and a group forming around him, Delduc, Lacroix, Magro, Vicedo, and so on, were developing this into a formalism which allows one first to describe a certain class of nonlinear sigma models on the classical level, to study their integrability, and to study things like one loop RG flows and so on, as we will now very briefly review with some specialization to the cases of interest for us here for this talk. So from the point of view of sort of somebody who has a bit of experience with integrable models, the point is simply to allow more interesting, less trivial dependence on spectral parameter. So one introduces a Riemann surface, here denoted C0 to n. We shall restrict attention to punctured spheres. There is more possibilities one can consider. However, for this business, this is the thing we know well how to deal with. And and then sort of a key object is the so-called twist function, and that is, to begin with, just a generating function, if you want, for the physical parameters. So we'll see on the next slide. So, well, what does it depend on? Okay, you can view it as a function of, here you see poles, right? So you can either fix the position of these poles and their residues, which will be called levels, or you can fix the positions of the poles and of the zeros. And the physical parameters, like what we've just seen, like for example epsilons, will then be given as functions of the parameters that we see here. The k is quite explicit, okay, and there was a zeta which also has appeared somewhere here already. There's a particular combination, so that is again not so important. Really, the key players for us are here these poles, which are really then physical parameters of the sigma models that are described in this way, and well, levels or zeros of the twist function. So yeah, this basically the complex analysis of these Riemann surface will code a lot of the physical properties of the theories that are described in this way. Now, the game proceeds as follows. To each of these poles, one associates a Kac-Moody current. Well, here we're classical. It's a so it's just where we specify sort of the phase space we want to work with by, well, here introducing Kac-Moody current for each pole and imposing a Poisson structure or defining a Poisson structure, which is the standard Kac-Moody Poisson structure for each of these guys at each pole. Then a key thing, key ingredient is to also introduce, well, a constraint, which then in the Hamiltonian framework has an associated gauge symmetry, and it will be just the same gauge symmetry as we've used before here in the description of the Klemtrik model once we specialize to it. So there's a constraint, has a very simple form in terms of the currents, and well, by taking Poisson brackets, it generates gauge transformations. So this concludes the description on the kinematical level. Next step, of course, is we want dynamics. Dynamics is introduced by introducing Lie-cone Hamiltonians, from which you can then form the true space time-like Hamiltonian and maybe space translation generator in the usual way. And yeah, again, sort of details maybe don't matter so much. So if you're not knowing this already, The main point being that really we're getting everything here by exploiting basically the complex analysis of this Riemann surface and the twist function. So for example, here we're having a generating function called gamma, which is playing the role or closely related to the Lax matrix here of these affine Gaudin models, which we can form out of these Kac-Moody currents and then here explicit poles. And then we're taking some quadratic expression of these gammas and taking invariant form on the Lie algebra and integrate over X in order to get something that depends on the spectral parameter. And then by taking residues, we're going to get, well, some phase space function, which by definition gives us the light cone Hamiltonians. So now we have dynamics for the models that are defined in this way. So we can just use it, consider it as a game for defining some interesting dynamical systems. Well, they are particularly nice because they're integrable. There's a zero curvature condition one can, again, say, write down with the help of a Lax pair. Here we're using light cone formulation from the start. And again, well, don't worry so much about the details if you're not so familiar with this. But the point is we're basically using just the same ingredients, namely twist function, Riemann surface, and currents associated to the poles in order to construct these guys. So we're evaluating here this Lax matrix gamma. This is the derivative of the twist function we're evaluating at the zeros. So these are functions of the physical parameters. And what comes out is a new collection of, say, currents or linear combinations of the currents we're working with, out of which we form the Lax matrix. Okay, I promised you that this is just some family of generalizations of the Klemtrik model. So here is the precise relation. If we choose this parameter m, what was m? M was counting basically the number of zeros or poles. Well, poles is a little more, so it's m plus 1. So if we set m equals to 1, which would correspond then to a twist function having 4 poles in total, and if we identify here positions of the poles with epsilon parameters through these relations, and the levels through these relations, then I can assert you that this construction would just amount to a description of the Klemtrik model in the Hamiltonian framework. All right, so far so good. Maybe quickly.
Can I just ask questions? I thought that there was some extra information that was needed, because the same twist function can correspond to different integral models related by some kind of duality transformations. So there is some kind of how to realize the currents in terms of the fields of the Klemtrik model is
that's true.
It is needed.
Yeah, that's true. I'm here glossing over sort of. I'm suppressing sort of that there is a zoo of further possibilities that one can play with. I'm presenting here a family of special cases, somewhat tailored to the story I want to tell, but there's a lot of room for generalization. So I think I cannot say much better things briefly, but maybe we can return to this. But in any case, this is what we want to talk about. Yeah, sometimes there are some signs here introduced which would give some discrete extra family of choices. And so, well, don't worry so much. I mean, for the moment, here's a definition, and it reproduces Klemtrik, but also generalizes Klemtrik, and there's probably a lot of room for even further generalizations. That's all I want to say. All right, so first step towards quantum theory is, of course, usually perturbative. And one of the beautiful features, as discovered in particular in work of Delduc, Lacroix, Svetsos, and Tsiampos, is that the one-loop RG flow of the sigma models, which are described in this framework, has a very nice description as a flow of this twist function, which of course will correspond to a flow of whatever appears as parameters in it, in particular position of poles and so on, will flow in the one-loop RG flow. There is a certain, in this formula, there appears a certain function, which I didn't bother to write down. The main feature for us, sort of for this level we're discussing here, is that it is just formed out of the twist function itself by a certain procedure. So it does not contain any other information than what is contained in the twist function itself. So that's already very beautiful. But then sort of a key observation for us, which we made by first looking at well, the Klemtrik model RG flow, where the answer is known thanks to Fatiev and others. And then, well, with some numerical checks, we observed that at least for low m, it seems to generalize, is that when we have twist functions of this form, which is somewhat special, because you see here, I say already separated poles and zeros into two subsets of equal size. And the point is, we observed that, yeah, in the approach to the RG fixed point, half of them, those with a plus, go to 0, and the other half goes to infinity. So somehow this already yeah, reflects something important that is going on in the approach to the RG fixed point. And that will be really very important for us, because it leads to the description in this context of AGMs of these, the theory in the UV, which, yeah, I think is a very useful thing, and which we want to take as the starting point for the quantum theory. So how does it look like? So first of all, one can here, well, to approach the fixed point, one can use this parameter zeta as a scale parameter and as a replacement in the vicinity of the fixed point for the running coupling. And yeah, then, well, again, details maybe don't matter so much. Really, the qualitative picture is simply that by a rescaling of spectral parameter, we can get basically limiting Lex value, Lex matrices. But then there's two ways of rescaling the spectral parameter. One by dividing sort of with the running coupling, and the other by multiplying with it, which gives us actually two limits, which on first sight may be surprising, but in the end, we will see this is exactly what we want, because this will correspond sort of to picking out the two chiralities that we expect to find, of course, when we go to an RG fixed point described by a conformal field theory. So this will just be corresponding to the left and right half of the theory we're finding at the RG fixed point. And the Lex matrices that are defined in this way describe the integrable structure of the conformal field theories we find at this fixed point. But yeah, just formally, you see then quite easily, just by working here with this AGM formalism, what's happening. Namely, the point is that in this particular limit, corresponding sort of to the left movers, up to gauge transformations, the minus part of the Lex matrix will vanish. So if you look at what the zero curvature condition, the one here, tells you, then is of course just it tells you that the L plus then must be chiral, so that you have well, that the matrix elements of this guy satisfy a chirality condition in that limit. Well, that's a simple consequence of these two findings up here about the RG flow. Well, furthermore, okay, I already mentioned there is this a second limit for the other chirality, and what taken together this amounts to is a dynamical decoupling of these two chiralities, which is of course just what we would expect. But the important thing is that now it finds in this formalism of affine Gaudin models a very simple and nice representation in terms of, well, these chiral Lex matrices L plus, depending on sort of the left spectral parameter, and then it has of course a partner where left is replaced by right and plus is replaced by minus. And as they decouple, we shall now focus just on a chiral half, and to simplify the notations, drop these left and plus in the notations. So we look now at the chiral affine Gaudin model representing an RG fixed point. All right, so this is sort of what I'd like to advertise as the strategy we want to apply to this class of problems, which I believe has a lot of potential for making progress on this type of problems. And to distinguish those sort of from the more traditional approaches which were running into the non-ultra locality problem, let me here draw sort of the caricature of the parameter space. So usually if you would do canonical quantization or various perturbative approaches, you would be expanding around the classical limit corresponding to h bar going to 0, corresponding to, say, 1 over k going to 0, or alpha prime going to 0, and so on. So here in this picture, it would correspond sort of to the bottom of this three-dimensional room in the parameter space, where we have parameters nu. Kappa is the running coupling, and we're plotting here 1 minus kappa such that, well, this left wall actually corresponds to kappa going to 1, so this is the conformal limit. So the proposal is really to sort of enter here from the side, namely from the conformal limit. I will try to convince you that this is a useful starting point for the quantization of such models, because it will help to describe the algebra of local observables and the quantization of the integrable structure. And the hope, but this is what I cannot tell you about in this talk, is that indeed there is ultimately a deformation away from the conformal limits. It follows the, I mean, this is of course closely related and inspired by this philosophy of proposed by Bajanov, Lukyanov, Somolochikov for, well, taking the integrable structure of conformal field theory as a starting point for understanding integrable structure of massive integral field theories. A, however, important point to stress is that, well, okay, even if we put ourselves here on that left wall, the non-ultra locality is not gone. It's still there, and we will later see where it hits us again. There is, of course, conservation of difficulties. But anyway, say approaching it through the lens of this AGM formalism will at least allow us to make a start here in the conformal limit. All right, so let's go into the business. And let's start from, well, a really enlightening summary of some of the techniques that have been developed for the quantization of chiral AGMs. That's what we now are talking about, and their quantization. And what we found by applying them to the case at hand, which is Klemtrik model and generalizations in the conformal limit. All right, I mean, on the kinematical level, life is relatively simple to begin with. We were representing the degrees of freedom in terms of currents. So what is easier than quantizing currents? So the classical Kac-Moody algebras turn into the usual current algebras, and we have now one for each of the, say, plus punctures, the plus poles of the twist function. There is going to be a constraint again, which we can also quantize. Of course, there are some things I'm not going into, parameters, for example. So the levels here are suffering some small but ultimately pretty well-known quantum corrections. So in any case, there's a gauge symmetry. Again, the generator is represented as sum over currents. And what this leads into is sort of a representation of the algebra of local observables by a coset VOA. So if we have here our M, say chiral or plus punctures, then this would be the coset we would be finding. In the case of Klemtrik, yeah, we have here two summons in the numerator and one, well, there's always just one in the denominator. So that's nice and simple. What is quite non-trivial and sort of a beautiful result of Lacroix, Vicedo, and Yang is that in this context, there is a beautiful approach for constructing local charges in involution in these quantized chiral affine Gaudin models. I don't really want to take the time to walk you through all the details here, but let me give you the flavor. The local charges, well, as usual, are constructed as integrals over some densities. The density, so this is the spatial axe we're integrating over, the argument of the density. This in turn is, however, the integral with respect to spectral parameter of something, some generating function depending on spectral parameter. And here's sort of how it is formed. Well, there's some explicit function which basically encodes parameters of the model called P of Z. And there's again a quantum version of this Lex matrix where we have poles and currents as the residues. And then the key thing to construct here is this density SP plus 1, depending both on spectral parameter and spatial position. And what you can do, that is sort of the conjecture, which of course was quite non-trivially checked by these colleagues here, is, you can make an ansatz here where, depending on sort of the weight of the local charge you're interested, you're taking here certain product of these Lex matrices, normal ordered, plus lower terms, which have lower number here of these factors, but may have more derivatives and so on. And the main difficulties, of course, to find this density. The conjecture is that this can be basically, well, or the family of those can be uniquely characterized by VOA conditions where one ensures gauge invariance. So it is basically formulated in terms of the OPE with this diagonal current, and the other, and there is an, well, basically necessary condition for OPEs of this guy here with itself, which would ensure commutativity of the such constructed local charges, which these people here were able to write down. So, okay, so this just sort of to advertise this beautiful results, which basically for us leads to a procedure, a well-defined like algebraic problem whose solution would give us the local charges. And for our purpose, we worked out in the paper, say the quartic one, which is already quite a beast. Anyway, so now, okay, I can't really, of course, summarize all the results that we have in our bit longish paper, but let me here now formulate in a schematic form, perhaps two of the most important. So it should be stressed from the very beginning that the model we're studying, and that is why it is useful sort of as a testing ground for approaches generalizing this story using the affine Gaudin formalism. So here we can, of course, draw on, especially the results of Bajanov-Lukyanov, Bajanov-Kutuzov-Lukyanov, who have studied these using the ungauged formulation that I briefly sketched at the very beginning. And now one of the points, of course, for sort of getting confidence in the approach through the affine Gaudin models, which is a gauged formulation by its very nature, we have carried out a rather detailed comparison of the integrable structures and their representation on the classical as well as on the quantum level. And sort of key elements of this comparison was, on the one hand, to compare the affine Gaudin model Lex matrix, once gauge fixed, which is a non-trivial thing to do, with a Lex matrix that sort of you would obtain from the ungauged formulation of Klemtrik, which was computed in particular in work of Bajanov, Kutuzov, Lukyanov in the chiral limit. And the non-trivial thing here to do is to compute the relevant Dirac brackets to really make sure that sort of the Poisson structure that one finds for the matrix elements is the same after gauge fixing as the one sort of that would be coming directly from the ungauged formulation. So that is sort of result number one, which for us was important. And the second was the comparison of the quartic charge. So basically following Bajanov, Kutuzov, Lukyanov, you would characterize it. It would lead to the characterization in terms of commutant with certain screening charges. And then what we did was to compare it with this construction here, which is importantly based on the affine Gaudin model formulation. All right, so let me come to applications of this, but maybe I quickly make a pause to see if there are questions which have come up. Doesn't seem to be the case. So I want to indicate two types of applications. So on the one hand, when we have a description of as AGM, and I think sort of a key, perhaps new, point of view that is coming from our work is this point of view to describe, I mean, in the conformal limit to notice that sort of these relativistic quantum field theories, non-conformal, that they indeed become chiral affine Gaudin models of exactly the type that Fagin and Frankel in their original work have been studying. And their main point was to come up with a certain class of these chiral AGM models with a conjecture for the description of the spectra of these models using what is called the ODE IQFT correspondence. So here in a nutshell, we can formulate the result as follows. So this would apply sort of to the class of generalized affine Gaudin models I've introduced. So it would say that there is a one-to-one correspondence between the eigenstates of the quantum affine Gaudin model and differential operators of a very peculiar type. There's one ingredient which we've seen before, some explicit function, just coding sort of the physical parameters of the model we are aiming to solve. And then there is a, say, variable potential in here, which is basically characterized by analytic properties, again, sort of essentially given by the choice of this Riemann surface that is sort of underlying the whole definition of a affine Gaudin model. So it is allowed to have second order poles at the poles of the twist function, and another set of singularities, however, with a peculiar and important property that the monodromy of this differential operator around the extra singularities should be trivial. And many of you will have encountered such singularities already. These are called apparent singularities. The triviality of the monodromy around these extra punctures implies algebraic equations for their positions. And this is expected to have a discrete set of solutions, which would then be, I mean, enumerating these solutions would be enumerating according to this conjecture, which has been extensively checked in various cases, would be enumerating the eigenstates of the chiral affine Gaudin model corresponding to this problem. But even better so, there's a beautiful formula which should remind you of this very formula here for the eigenvalues corresponding to the eigenstates. Namely, what you are doing is basically to perform a similar integral as what was giving us the conserved quantities. However, now you feed in here a certain explicitly understood, or I mean, there's a recursive construction, a certain differential polynomial that you form out of the solution to this problem here of complex analysis to find the differential operators which have trivial monodromy around the apparent singularities. So you feed it in, you compute an integral, here's a number, the eigenvalue. All right, so that is application number one. So basically what this suggests is a, yes, please.
May I ask a question about this point, because you go further? But this kind of formula can be derived using this differential operator, can be derived using substantially some WKB method, I guess, no?
I mean, this differential, I mean, you can apply WKB to this differential operator, and this gives you interesting information and can help you sort of saying something interesting about the solution to this problem. But to find this differential operator in the first place...
No, I was referring to the integral. How do you find this I gamma P? This is my question.
Well, the formula for I gamma P can be motivated using the WKB expansion, because in some sense, well, this here will dominate. Will
you expand
P will dominate the leading term and so on, and it is useful therefore to uniformize the spectral parameter surface with something defined in terms of this P function. These are, I mean, okay, there's a beautiful story here, which I don't have at all the time to discuss, which is also what other people have studied extensively. So is it perhaps a reasonable suggestion to postpone this maybe to later discussions?
Okay, thank you.
Yeah, it's beautiful and important, but okay, I just here wanted to make the point that basically the same ingredients that we've seen before in the end allow you to compute eigenvalues, even though I don't have the time to really go to any further details about how this works in practice. Yeah, I mean, okay, if you give me 4 to 5 minutes, I can say a little bit about non-local IM and maybe return to non-outer locality at the very end, and then I will conclude. I'm already close to the end. Namely, we can turn sort of things around now. So we have basically, using the results I've stressed here, gained some confidence that gauged and ungauged formulations of these models are really equivalent, fully classical and quantum and so on. So a trouble in the AGM formulation, which to the best of my knowledge, hasn't been overcome up to now, is that, well, even though there are, of course, ideas how to construct non-local IM, that's pretty straightforward, I don't think there exists a proof of commutativity, especially in quantum theory of the non-local IM, in the AGM formulation. Now, there's a remarkable conjecture that Bazhanov, Kutuzov, and Lukyanov came up in 2018. And now sort of understanding a little better the relation between AGM formulation and sort of ungauged formulations, we can carry it over essentially to say AGMs, and it makes a remarkable prediction I want to briefly discuss. So, but what did Bazhanov, Kutuzov, Lukyanov propose? There's actually ongoing work with Gleb and Sylvain, where we're trying to understand it better, and we're hoping, say, to be able to prove at least the most essential part of this conjecture. What it does is it starts from, say, two very important key ingredients, which are called screening charges. These are basically really nothing but the quantization of what has appeared here in this Lex matrix. We have seen these guys before. We need to quantize, okay, that's a bit of blah, blah, and so on. We have to discuss, but I don't have the time. Anyway, these are pretty standard objects which which are basically, yes, naturally appearing in the quantization of the Lex matrix in ungauged formulation. Now, a fact that I think we can prove, so our paper with Gleb and Sylvain contains the idea, a sketch of the proof, is the following. We can form polynomials out of these integrated screening charges, and out of these we can form something that you can interpret as a basically renormalized version of a quantum monodromy matrix. That's the upshot. So, okay, again, I don't have time for details, but the point is this can be defined as a formal power series in parameter lambda, and then monomials or polynomials formed out of these ingredients x0 and x1. And one of the key subtleties is that even the products here, I mean, the construction of monomials requires some renormalization. Well, relatively standard one does the job, but what is non-trivial is whether this indeed in the end can be done in such a way that the upshot satisfies Young-Baxter. I feel very confident in this fact because once one has shown that x0 and x1 properly renormalized satisfy Serre relations, one can rely on previous results of Bazhanov, Lukyanov, Solnochnikov, and Bazhanov, Koroshkin, Hibbert to arrive at this statement. So that is, therefore, I'm confident that this statement holds. The formal power series, which is somewhat symbolically here written as a renormalized path-ordered exponential, satisfies Young-Baxter. But then the main point of the conjecture of Bajanov, Kutuzov, Lukyanov was that this admits a classical limit. And that the classical limit, that this thing here, which is now a perfectly well-defined, perfectly rigorously defined mathematical object, that this can be cast in the form of really, a path ordered exponential of a Lax matrix we've seen before, namely the one which was appearing here, exactly this guy. Where, however, the non-trivial and interesting thing is there's renormalization of the spectral parameter. So what appears here, Z was the spectral parameter of AGM, is a non-trivial function of lambda, the spectral parameter here. And that is sort of the remarkable thing. It already indicates that something quite tricky and subtle is going on in this limit. Okay, so yeah, this limit is a subtle one, and so we're hoping to be able to really rigorously establish the existence of this limit, and thereby, on the way, understanding quite precisely sort of these scheme dependence, which determines the function z as z of lambda. If, however, this is established, then indeed, to my mind, it justifies to call the M of lambda, the thing which is here perfectly well defined, to call it quantum counterpart of the classical monodromy matrix, which satisfies Young-Baxter. And that, after all, was always the problem with non-ultra locality. I mean, this guy here, okay, this I should have stressed. The Poisson bracket here has the same problem as before. It has the delta prime, non-ultra locality strikes back, and so on. So if we would start here from the conventional point of view, trying to set up a Poisson bracket for this type of monodromy matrix, we would be running into the same troubles. However, this here indicates a possible way out, which is purely quantum. In fact, at the moment, at least, it's unclear if this thing here would satisfy an equally simple Poisson bracket like the classical Young-Baxter equation, because at the moment, we're not 100% sure if, say, due to these renormalization issues and scheme dependence issues that do appear for sure in that limit, whether the simple quantum algebraic relations really lead on the classical level to a simple Poisson algebra for this guy. Anyway, it suggests that the construction of non-local IM in quantized affine Gaudin models can also follow the Young-Baxter paradigm, which I think is somewhat unexpected from the point of view of affine Gaudin models. So there's ultimately, it seems there's emerging perfect harmony between these 2 points of view. And this is what I'm trying, so I'm really over time, I'm sorry. But here, that's my last slide on which I want to emphasize sort of the hidden structures that this point of view uses and reveals. AGM formulation in particular reveals affine Lie algebra symmetry, which is good for quantization of the algebra of local observables and the construction of local conserved quantities. Very important is sort of to use and understand sort of what one learns about complex geometry of the spectral parameter surface, because it helps understanding RG flows, the construction of local IM, and through the ODE IQFT correspondence, the spectra. And furthermore, the relations to the quantum affine algebras ultimately give us hope, or give us hope to understand non-local integrals of motion as well. And good, I can't help concluding with the sentence with a hope that this is not all peculiar to the conformal limits, but even deforms, as we know it does for other classes of integrable quantum field theories, away from the conformal limits. Okay, that's it for now. Sorry for going over time.
So, questions? Maybe I can start. I wanted to ask about reality. So quite early on, you had the Klemtrik model, and you had these factors of I in the action.
Yeah.
In front of epsilon. So this model is I guess not real for G bigger than when the rank of G is bigger than 1. or for at least?
Oh yeah. There are certainly issues of this kind. Indeed, as was not said but written here on the slide, we're restricting to the SU2 case, which is indeed well what this applies to, where indeed we have a proper sigma model interpretation with real fields and so on.
So I guess my question is the other regime. There's another regime where I guess epsilon 1 and epsilon 2 are would be imaginary, where you get this cyclic RG flow and all this weird stuff. Does this construction that you have, do you think it would teach us anything about that regime, or for example, in the case of strings, when the dual Coxeter number vanishes, there is no RG flow. You could hope somehow still to learn something.
Yeah. Okay. I think we made a few remarks in the conclusions to the effect that we would hope that this perspective shed some new light on these cases as well. But okay, to be honest, we didn't really seriously analyze those, and so we will have to leave it for the future at the moment. Yeah, I cannot really say.
And did you also look at this, I guess it's called lambda model, but some kind of current deformation of the Westerminer-Witten for S?
Yeah, I mean, yeah, I hesitate to offer you. I mean, yeah, we looked a little bit, but in the end, sort of, we don't have as yet. But okay, we didn't really try hard. A kind of very clear story to tell about these cases as well. So again, there is something probably quite interesting going on, because yeah, I mean, if you look more closely to the sort of the details of this story, one finds something remarkable related to this relationship between the W algebra representing the degrees of freedom, which is a coset W algebra, which you can alternatively characterize in terms of screening charges and so on. And the screening charges, in turn, they would correspond sort of to the leading interactions in this UV limit. And well, all this is something that we looked into rather closely and in great detail for this model. And well, there is an observation we made in our paper about some kind of symmetry of the integrable structure with respect to, well, a replacement of the screening charges, which are relevant and describe the UV limit for this particular case, to one which might have something to do with the coset model, because in some sense, this coset model, yeah, I mean, here, it's in fact a little bit from the point of view of this ungauged formulation, a surprise that we're finding the coset VOA as the relevant VOA. That comes basically as a mathematical accident for that model, whereas for other models in the realm that you mentioned, it may be more natural. So, well, I guess I just want to sort of encourage people to look into this again, maybe with a sharpened eye, or with an eye sharpened from a look at this particular example that we think we understand better now.
Thank you.
Joerg, does this technique help to understand better, I don't know, the O3 sigma model with theta term? Can you, for instance, spot if something particular happened, theta equal pi, if it's integrable, what's going on there?
Well, hopefully, ultimately, yes, but right now, not yet, to be honest, right? So because we're not yet conformal, and yeah. But of course, yeah, I know these are related. We could flow to the UV. Perhaps something can be carried over from Of course, here, this kind of squashing is important, that is reflected in the epsilon parameters for having a particularly transparent description of the UV limit, basically in terms of, well, in particular here, well, I didn't say it, these are Witten cigars, right? So SO2 over U1 cosets, and so on and so forth. I expect something can be carried over maybe to something like O3, but yes, we're not there yet, so I shouldn't say more than that.
So it seems that you are arguing for quantum integrability, which based on several like conjectures. Could you kind of recap like what the assumption, what the conjectures / assumptions are, and for each one, what was the evidence for that?
Yeah, okay, right. Thanks for asking. In some sense, okay, I try to be honest and careful, so marking what in the end of the day is a conjecture as a conjecture.
Yes.
I think the first important one is this here, the form of the local charges, where of course in that work there are very non-trivial checks by calculating examples, and if you look on how that works, well, at least I think it looks quite convincing, but yes, as far as I know, it isn't yet a mathematical theorem. On the other hand, let me point out one of the things giving a lot of confidence in that this must be on the right track, which is exactly this remarkable relationship with the ODE-IM correspondence, right? So you can kind of independently think of what would be the most natural candidates for how to compute the eigenvalues. Well, the WKB method was mentioned already, and it would lead to formulae like this. And this has been, this type of formula has been checked already, well, by a lot of explicit computations in, say, the Klemtrik case in work of Bajanov-Lukyanov and so on. So by now, I would say, even though sort of there are several things, well, the very ODE IQFT correspondence is a big conjecture in that field, which is very important. But on the other hand, I think the evidence that has been accumulated, to my taste and maybe many others, does not leave much room for, it does not leave much room for doubt that this is completely off and completely wrong. So there's so many like detailed computations which check the most relevant conjectures in special cases that that you just need to, well, like extrapolate a bit, and then you have a very yeah, complete and nice picture. So, and yeah, here
so,
about
so
this
ODE-IM stuff you presented as application, but your point is that you can actually use it to motivate the conjecture as well. So in a sense, the argument go both directions. Is that
yeah, you can turn it in different ways, but here sort of the point I wanted to stress is simply that the perspective that we've put forward, namely to look at these AGMs in the conformal limit, if you then just use these observations about how conformal limit works here, namely by basically this separation of the poles and zeros into two halves, which go to 0 and infinity respectively, leading to decoupling and so on, then yeah, it immediately basically gives you a kind of recipe for well, what the relevant conjecture. So for given a sigma model, basically this gives you a recipe for what will be the ODE IQFT conjecture you want to use. And thereby, in a sense, it makes a prediction for the solution of the model in the conformal limit. I mean, even those, say here, which are generalized Klemtrik models, of course, yeah, here is a very natural, like, conjecture what the solution should be, simply by, yeah,
I see. So coming back to the assumptions, then once you accept the expression for the charges, and that's basically, I mean, the statement of integrability itself, I guess.
Yeah. So I mean, okay. So here, in some sense, yes. So what this ansatz here, I mean, what this. Okay. So there's of course more, right? So really here, this crucial result. So what they show is that you can write down VOA conditions. Well, a simple one about the OPE of the diagonal current with this density, and a more complicated one about sort of the OPE of this density with itself. So you can formulate conditions that just are formulated, are like structural conditions on the form of the OPEs, which would ensure that this construction gives you gauge invariant objects and objects commuting with each other. And in this sense, well, I think in any case, it's a big step forward. What is, of course, the hard part, which is part of sort of what is meant here by the conjecture, is that, well, you're getting all local charges this way. And, well, also you have to basically classify the solutions to the problem that is formulated in this way. That would amount to a full description of a set of generators for the algebra of conserved charges. That is not yet, strictly speaking, available. Of course, on the other hand, you see here clear parameters to play with that this ansatz has, which is the choice of a contour on that surface defined by the twist function and well, some spin basically of the local charge.
Thank you.
Hi, Jörg. I wanted to ask if your analysis works in the same way for supergroups. Because if I understand correctly, okay, the conformal limit in the case of Lie groups corresponds to Vesumino models. But I suppose that for supergroups you also can have a conformal limit where which is something else than a Vesumino model.
Yeah, this sounds like an exciting direction for the future. At the moment, I think all this is sufficiently new, and yeah, I don't have anything reasonable to say. It sounds very interesting idea to look into this, but I cannot really say anything at this moment. Sorry.
Hi, still Davide speaking. So this is connected with my previous question about WKB. It's just a curiosity, but since now we have some understanding, little understanding about ODEM also for massive theories, of critical theories. I was wondering if you thought about the possibility to have instead of this offer something which works for the theory outside the conformal point.
Sure. Sure. There are, and that is, I think, one of the most prominent results of the work of Bajanov-Lukyanov I was referring to here. For the Klemtrik case, there is a conjecture already for how to deform this business here away from the conformal point. And then, yeah, things are no longer holomorphic. You're replacing this by the corresponding modified Gaudin model. And so on and so forth. So there is a conjecture, and I think, good. I think it's kind of obvious thing to state when looking at this now from the kind of new perspective that we've gained. Yeah, there should be generalizations of that, and perhaps what we can tell here indicates where to look.
Great. I think we're a little bit over time, so let's thank Joerg again for his talk.